Go ahead.
Okay.
Yeah, I think Aamir will be starting.
Yeah, Aamir will be starting. Okay. Aamir, can you see the slides?
I can. Are you ready to go?
Okay. So,
Sure.
yeah.
Okay, so good afternoon, everybody. So this in this talk, we'll be talking about high performance machine learning and deep learning project at OSU. So next slide, please. So here is the outline. We'll introduce this project, and then mainly this work is spanning two areas: machine learning followed by deep learning. So I will kick off and present the latest developments in machine learning, and after me, Nawras will cover the recent developments in the deep learning area. Next slide, please. So this cartoon here essentially shows the evolution of AI and into machine learning and into deep learning. Our work at OSU spans both machine learning and deep learning. We have worked with a variety of workloads, optimized their performance using MVAPICH, and in this slide deck, we'll be talking about that. Next slide, please. So just a little history, of the development of MLDL. Some of the names that we hear, like linear regression, Turing machines, they have been around for a long time. But recently, since the uptake of ResNet, ImageNet, and AlexNet, so in around 2012, deep learning has seen a re-emergence essentially, and things have drastically changed with the evolution of transformer models. So our work, the work that the project that we are covering in this slide deck is a high performance deep learning, and this started around 6 years ago. And the project has also evolved, and essentially the latest work that we are doing is also optimizing performance of training inference of large language models, which are GPT based. Next slide, please. So with this now, I'll move towards some of the latest developments in the area of machine learning. So traditionally speaking, machine learning, the traditional machine learning spans three areas: supervised learning, unsupervised, and reinforcement learning. Traditional wisdom typically has been that machine learning doesn't require a lot of compute cycles, but deep learning, neural networks or deep learning is different because the models are so huge. There are so many parameters, and we need a lot of compute cycles to process them. However, the data is becoming so huge now that HPC is also a viable option for traditional machine learning algorithms. So next slide, please. So in this context, some of the frameworks, they already exist. So for example, scikit-learn. This is a popular machine learning library, supports distributed computing, but only has support for CPUs. There is another gradient boosting library called XGBoost. This again also supports execution on parallel and distributed systems, relies on some big data processing frameworks like Dask, Ray. What we are particularly interested in here is the QML project. So this basically makes use of multiple nodes. So you are able to scale out essentially using a Dask and NVIDIA's Nickel communication library. Next slide, please. So in terms of QML, one of the particular algorithm, QML provides GPU accelerated algorithms for popular machine learning algorithms. But one of the popular ones out there is obviously k-means. And in k-means, we are essentially trying to classify data, trying to identify patterns in them. And I wouldn't go into the details of this figure, but in terms of doing all parallel and distributed processing and all reduce collective communication method is required. So the data communication is not huge because we are not during every iteration we are only sharing the data points which may not be that you know, may not be huge in terms of the volume of data, but still there is, all the processes need to sync, and we need to make sure that this is an optimized operation. Next slide, please. So we'll now briefly talk about some of the solutions that come out of our lab as part of the HiDL project. So this is an introduction of QML library. So this comes out of NVIDIA Rapids project. The goal of the project is to build end-to-end data science pipeline entirely on GPUs. And this is, the QML library is an important, the important components include, the library itself. It's the GPU counterpart of scikit-learn, and it supports, parallel and distributed execution of ML workloads in a distributed settings. As I said earlier, that most existing communication ML libraries only support CPU, like scikit-learn, Apache Spark's MLlib, but QML is trying to do the same thing on the GPUs, the GPU ecosystem. Next slide, please. So here is a detailed, breakdown of what the QML is. If you look at the top figure here, at the top we have the Python layer followed by algorithms. So some of the popular algorithms are already implemented by QML, but if let's say your favorite ML algorithm is not present in the QML library, some primitives are also exported. So you should be able to work with primitives and implement your own algorithm as well. In terms of support for parallel and distributed computing, if you look at the bottom figure, a UCX communication library is used in combination with Dask. Dask is a big data processing framework. And then, during the execution of algorithms like k-means, when iterations are going on and collective communication is required, Nickel is also essentially supported. Next slide, please. So what we have done as part of this work is that we have, the Nickel support stays there, but we have also added support for MVAPICH2 GDR into the QML stack. And we basically do that using Python binding. So we have used MPF4Pi, which is a popular Python MPA library. And, we use the interface between MPF4Pi with MVAPICH to implement to provide supports for collective communication using the MVAPICH library. And this work is encapsulated in, this has been released, publicly released. Next slide, please, Nawras. So it's the latest version out there is, 0.5. We call this MPF for QML. So all the benefits of QML stay, but, you're now able to utilize, on top of using Nickel, you could also utilize MVAPICH GPU-based communication in this library. So in the next slide, I'll just briefly give an overview of some of the performance numbers that we have seen. So for example, let's just focus on top left here. We have the k-means, x-axis is the number of GPUs, y-axis is the training time, and we are basically comparing the performance of, training k-means using MVAPICH2 GDR versus Nickel. And, we witnessed around 1.6x gains just by changing the communication stack. And we also see similar trends for other algorithms, for example, linear regression, nearest neighbors error, and truncated SVD. So with this now, I'll hand it over to my colleague Nawras, and he'll cover the deep learning part.
Okay, thank you, Aamir. Just pull up the laser pointer here. Okay. So yeah, this next part is about deep learning, and I believe most people in this room already know what deep learning is and how DNN training happens, but let's cover a very brief background of the basic concepts about DNN training, and then we'll go into the distributed deep learning and some of the DL solutions that are part of the HiDL project at NowLab. So this is a very simple example of DNN with 3 layers. So in here, we don't count the input layer. So we have 2 hidden layers and the output layer, 3 in total. And DNNs are simply just mathematical functions, right? It's a function that takes input and gives you an output. And then parameters that you can tune or you can update are coefficients of variables inside that mathematical function. So basically, if you give the function an input and you see the output that is not exactly the correct answer, when you update your weights or parameters, you are changing the internals of this mathematical function so that in the future, if it sees a similar input, it will give more of an accurate answer. And this happens in two phases. The first one is the forward pass, where we simply take the input, we propagate it to the layers, and then we get an output. Then based on that output, we calculate the error or the loss. And based on this loss, we're going to do the backward pass. That is, let's propagate the error back to all of the network and calculate the gradients, which will tell us, okay, how much should we change these, or in which direction should we change these weights in order to make it more accurate. If it sees similar input in the future, it should give us a better answer. Some of the other important concepts here are the learning rate, and that is, okay, when we do these updates, when we perform these steps or iterations, how large of an update should we make? So the gradients will tell us the direction of the update and will tell us also in part the magnitude of the update, but the learning rate will scale this update. So how much should we update the network based on a batch or a single sample of data? So that's very important to pick the right learning rate. If it's too low, you need too many steps to converge to the to a minimum value, a minimum loss value. If it's too high, you might never converge to the minimum. But if you pick the learning rate to be just the right value, you will reach the basically conversions criteria within the least number of steps. Another important concept is batch size. So let's assume we have a data set of, I don't know, 1,000 samples, right? So N here is 1,000. We have different learning algorithms based on the gradient descent algorithm. One of these is the batch gradient descent, where the model will see all of the data set before making an update. So it will see the entirety of the data set, will perform the forward pass, the backward pass, calculate the gradients, and then update. And then we have stochastic gradient descent, where we randomly select a sample from the data set. We do the forward pass, the backward pass, calculate the gradients, and we update based on this single sample. So you can see the difference in the number of steps here for the same data set. If it's batch gradient descent, there's one update only for the entire pass on the data set. If it's stochastic gradient descent, it's going to be 1,000, so n time updates. And then we have something in between. That is the mini batch gradient descent, which is the, I'd say, like state of the practice. So in here, we pick a batch size, usually a power of 2, 64, 128, 256. And then we randomly select data from the data set, data samples from the data set. We form these batch sizes. We do the forward pass, the backward pass, calculate the gradients, and we update the network based on the data within this mini batch. And then we do this until we do a full pass on the data set, and that is called one epoch. But training usually involves many, many epochs until we reach the convergence criteria. Now moving on to distributed deep learning. So we just covered the background of DNNs on a very high level. Why do we need the parallel or distributed training? So one of the major reasons why we need it is that the models are getting larger and deeper. So for example, for language models, we started with RNNs, and then transformers came in 2017. And now we have these huge language models, a BERT, GPT, Llama, where we see models on the order of trillion of parameters. Same thing for the vision models. So we started with AlexNet in 2012, then ResNet, NASNet, MVAPICH2, all of these are CNNs, convolutional neural networks. And now we have the vision transformers. We're also scaling them to many million of parameters, hundreds of millions of parameters. So we see that there is a trend, right? Models are getting exponentially larger. The reason is the larger the model is, this is the trend that we're observing. The larger the model, the better the accuracy, especially if you have a lot of data to train on. And these models, as they get larger, they require more memory, they require more compute, and also the data sets are getting larger. So that means the processing time is getting longer and longer. So single GPU training is infeasible, right? It will take very long time, or even it might not work, right? The model might not fit in the memory of a single GPU. So community has moved to multi-GPU training. So if you have many or multiple GPUs on the single node, let's say 8 or 16, you can distribute the training on these GPUs within the same node. But this can scale to like a certain point, right? There is a limit. So that limit is how many GPUs can be fit on a single node. So that is why we need distributed or parallel training, where we do multi-node training. So cross nodes, and each node might have multiple devices, multiple GPUs in it. To achieve parallelism, or to distribute the workload across multiple devices, we have multiple schemes. Perhaps the most popular one is the data parallelism, where we simply replicate the same model. So in here we have 4 machines, and we're replicating the same model exactly the same weights on these 4 machines. We feed each machine different data samples, and then we synchronize these models. This works very well if the model fits in the memory of a single GPU. But now, what if it does not? What if it's too big to fit in the memory of a single GPU? That's when we need more advanced techniques like model parallelism, pipeline parallelism, where we split the model or the operations within the model, or even the input, so the sequence or the image, we split it across multiple devices, and we process different segments on different machines. And of course, we can have hybrid parallelism, where we combine multiple parallelism schemes at the same time. So I'm going to go over data parallelism very quickly. Again, data parallelism is the simplest. It works well if your model is small enough. So it starts with data propagation. So you have a batch of data, and you distribute that batch to different devices. In here we have 4 GPUs. So each GPU will randomly get different data samples. And we'll start with the same model parameters on each GPU. So all of the GPUs will start with the same, basically, replica of the model. And then we'll do the forward pass, we'll do the backward pass and calculate the gradients. But since this model, this GPU is seeing different data, GPU 0 compared to GPU 1 and the rest of the GPUs, we end up with different gradients on each machine, right? And we need to synchronize these gradients in order to have the same model on all machines in the next iteration when it sees new data. So that's why we need like a synchronization operation. In this case, it's MPI or reduce, where we take the gradients from all of the machines, we sum them, and we broadcast them back, and then we take the average. So in this case, we end with the same global gradient on all of the machines, and only then we use these gradients to update the model parameters and proceed to the next training iteration. Now let's move to some of the DL solutions that are part of the HiDL project. So this is the link if you're interested in learning more about the HiDL project. So maybe I'll move to the next slide. Yeah, so this is the HiDL software stack, release version 1. It is based on Harvard. We offer optimized support for MPI controller and deep learning workloads with efficient large message collectives like OR reduce on different CPU and GPU architectures. We support GPU direct algorithms for collective operations. And in addition to fork safety, we also exploit efficient large message sizes for collectives. And most importantly, is the portability, right? So you can take the stack and deploy it on different systems because it is based on the MVAPICH library, which is portable. So you can, if you have like InfiniBand adapters or Ethernet-based system, CPUs, GPUs, AMD, Intel, NVIDIA, it should be compatible with all of these different architectures. These are some performance numbers compared to nickel. So this is MVAPICH2 GDR compared to nickel. And in here, we can see MVAPICH at least matches nickel, and in some cases, it outperforms it on up to 16 A100 GPUs. And this is with the RICL library on the AMD GPUs. Installation and running is very simple. It's a single command. Of course, after exporting all of the MVAPICH variables, it should be just a single command. We offer a detailed user guide on the IDL website. And then this is a sample run. This is on a single GPU with the ResNet 50 model, batch size 64. And we see the throughput here, 334 images per second on a single GPU. And then in here, we see the command using MPI run on 2 GPUs, same benchmark, so same model, same batch size. And we see almost double the throughput, so 1.89x on the 2 GPUs. So very good scalability. This is another study where we go to a much larger scale, up to 15K GPUs on the Summit system with TensorFlow. This is the ImageNet data set. So we have 1.2 million images, and the model here is ResNet 50. And to train ResNet 50 on ImageNet, usually it is ran for 90 epochs. So in the entirety of the data set, we pass it 90 times. And then with this study, we see that going from 1 GPU to 15K GPUs, we were able to reduce the training of the entirety of ImageNet on the ResNet 50 model takes only 4.5 minutes. And this is a similar study, but on the Frontera system using CPUs. And here we see basically the exact same benchmark, but done in 7 minutes. So if you have access to a lot of CPU nodes, you can also use them to accelerate the training. And then this is a study on the lightweight models. So if you have models that underutilize the GPU resources, so right now we have these A100 and H100 GPUs, which are very powerful, but models that are considered now small, like there's ResNet 18, ResNet 50, ShuffleNet, they do not fully utilize the cores on these powerful GPUs. So, and if we do like data parallelism across GPUs, we will see good scaling, but we will see poor utilization on the single GPU. So that is why in this study, we further exploit data parallelism and that we place multiple models on the same GPU. So now instead of 1 replica per GPU, we place multiple replicas per GPU, and we see very good improvements up to 30%. This is the ResNet 18 model, and 62% with the ShuffleNet model, which is on the smaller side. Now, all of the solutions that we covered so far are data parallelism, but let's now talk about model parallelism, where the model does not fit in the memory of a single GPU. And here we have a study on the digital pathology. So we have these very huge images, right? 100K by 100K pixels. and we need to perform some sort of a computer vision task on them. So maybe classification, but we care about the details, right? The small details within the image. And we don't want to segment the image itself because in that sense, we will lose context, right? So that is why we need models and training techniques that support this type of data, very huge data that will require a lot of GPU memory. So this would never fit in the memory of a single GPU. Even the best GPU will not be able to accommodate this large message size. So for this, we have MPI4DL. It's also available on the HiDL website. And it offers a lot of different distributed training techniques like model parallelism, spatial parallelism for high resolution images, memory efficient bidirectional parallelism. It is based on PyTorch, and it is mainly the purpose of this package is to support very high resolution image training. And then you can also combine these different techniques, right? So you can use spatial plus layer parallelism. So in here we have some performance numbers. This is on the AmoebaNet model with image size 1K, and in here we have 2K. So this is comparing pipeline parallelism, plain pipeline parallelism, to spatial plus pipeline, which is supported in the MPI4DL package. And we see here the basically better throughput. So this is showing throughput. And then this is comparing spatial parallelism with spatial plus bidirectional parallelism. And we also see the almost double the throughput here. And then finally, this is on the inference size. This is the ParaInfer X package, which is a temporal fusion framework for LLM inference. And the idea here is, as the inference request, if you deploy a large language model and you want to do inference on it, as the requests are coming in, can you basically insert them into the inference pipeline instead of waiting for the previous batch to finish computation? So this is the idea of temporal fusion or in-flight batching. And in here, we are comparing different model architectures, large language model, GPT-J6B, Llama 13 billion up to 65 billion parameters. And then we can see here in the orange, the speed up over the faster transformer library. And then in conclusion, we are all aware of the exponential growth of machine learning and deep learning, both frameworks, models, data that is available. And we see that this presents a lot of issues, especially when it comes to computation and memory. And communication, of course. So in this talk, we presented some of these solutions, and we also pointed to the HiDL website. So if you are interested, please visit the website, and you can browse these different solutions. And if you have any question, of course, you can email us anytime. And then with that, Aamir, do you want to add anything?
No, thanks, Nawras.
Okay, thank you very much. Do you have any questions?
There's a question on the chat.
Yes. So the question is, when you assign data to the different GPUs, do you consider any load balancing strategy? So yes, usually when we distribute the data across GPUs, we distribute the same number of samples. So let's say we are dealing with images, right? And images are usually resized to the same size, right, across all of the data set. And then let's say the batch size is 1K, you have 4 GPUs, you're gonna split the number of images evenly between all of these GPUs. So you have exactly the same workload on all of the GPUs. So if you have a homogeneous architecture, GPU architecture, meaning all of the 4 GPUs are of the same architecture, they should synchronize, right? So they should start at the same time, finish at the same time. But sometimes you have like exceptional settings where you have heterogeneous architectures, or maybe you are indeed distributing different data samples to different machines. In that case, yes, you need to apply more advanced workloading strategies. All right. Any other questions? Sure. Okay.
Okay, so let's give thanks to Nawras and Aamir. So now we are into the final session. So we'll go through a set of short talks. And as I indicated earlier, like these are some of the work in progress. And we just want to make you aware of these are in the pipeline. And tomorrow also in my roadmap talk, I'll point to some of these presentations to see what is happening in the MVAPICH project as coming. So we are 5 talks. And we'll compared to the program, I believe we have done a little bit of reordering because some of you will be going to the OEC facility tours and some of the students will be driving them. So we'll start. So you are starting. So let's start with the Nawras. So this is again on the ideal work. As I indicated in the morning, this will be actually, this paper has been accepted at the Hot Interconnect conference. We'll be formally presenting at the Hot Interconnect conference on Wednesday, I believe. But here you will get a short preview.
Thank you, Dr. Panda. So this work is on the characterizing of communication and distributed parameter efficient fine-tuning for large language models. This is also known as PEFT methods. And the idea of fine-tuning is taking a model that is pre-trained on usually a very large data set. So let's say you have the Llama model, Llama 3, and it's pre-trained on a lot of data. And then you take this pre-trained model and you fine-tune it on a specific downstream task so that this model performs better on this specific task. And there are so many different ways to do this fine-tuning process. So this study aims to basically profile the different fine-tuning methods, especially in the distributed training settings. So we're going to start with the introduction motivation, review the evaluation methodology, and then we'll conclude this work. So again, this is a very condensed summary. If you're interested, please attend our Hadai talk on Wednesday. But the main motivation of this is that distributed training for LLMs can lead to significant communication overhead, especially if you're training a large model. So in here, we're showing fine-tuning on 32 GPUs, A100 GPUs, and we see that the scaling efficiency is around 81%. Let me pull up the laser pointer quickly. So here, going from 1 GPU up to 32 GPUs, we see that the efficiency is 81%. So due to communication, we have around 20% basically degradation in the performance. And if we look at the breakdown of the single iteration, fine-tuning iteration, we'll see that as we go beyond 4 GPUs, so 8, 16, 32 GPUs, we see that the communication overhead becomes much larger. So this orange in here is the communication overhead, and then red is the overlap between the training and the communication. And then the reason that we see this jump in the communication overhead from 4 to 8, by the way, this was trained on Ascend OSC system. Within the node, we have NVLink. Across node, we have InfiniBand, so we have a drop in the bandwidth. And that is why we see this increase in the iteration time. Now, this is using the full fine-tuning method, which means you're going to update all of the model parameters. But there are these more advanced techniques that are called parameter efficient fine-tuning, where we freeze most of the model parameters and only update a small subset. Or in some cases, we create new parameters and we update only these new parameters that we created. So this is the process of fine-tuning basically the full model where we have the pre-trained weights. We we calculate the weight update, delta W, and then we apply it to the original parameters of the model. So in this case, we have basically the full calculation, right, on the entirety of the model parameters. Whereas with PEFT methods, we basically create these two matrices, B and A, which are much smaller. But if we multiply them, we're going to get a matrix of the same size of the model weights, right? And then we only update these smaller matrices, right? So we calculate the gradients for these smaller matrices, we update them, and then if we want to use this model for inference later, or even in the forward pass in the next training iteration, we simply multiply these two matrices, we add them to the pre-trained weights, and we do a simple forward pass. So this is how it looks like for PEFT methods, especially or specifically LoRa, with DDP, distributed data parallelism. So we've seen this figure just 5 minutes ago, where we have the data set on the file system. We distributed on the different GPUs to mini batches, right? So we have mini batch 0, mini batch 1, and we have the model parameter, a replica of the model parameters on each GPU. We freeze most of these model parameters, and only some of them are active. And then we do the forward pass. The forward pass requires all of these model parameters, both frozen and active parameters. We calculate the loss. And then during the backward pass, we save on some of the computation because we do not need to update all of the frozen parameters. So we still need to calculate the gradients for all of the activations, but not for all of the weights, only the weights that we want to update. We end up with the local gradients, we do the O reduce, and then we have now the global gradients, and then we perform the weight update and proceed to the next training iteration. So for this profiling paper, this is what the setup looks like. We have the HPC system on the lower layer, and then above that, we have the different communication libraries and some of the DNN kernel libraries. And then we have the distributed training middleware. In this case, we use Torch Distributed and Hugging Face Accelerate. And then we have the deep learning frameworks, including PyTorch, Hugging Face, and Hugging Face PEFT, parameter efficient fine-tuning. And then on the very top, we have the application itself, which is the LLM fine-tuning. And then for profiling, we use different tools, including Torch Profiler, OMB, OSU Micro Benchmarks, and TensorBoard. So here are some of the numbers from the paper. This is the experimental setup. Again, this is on the Ascent system, OSC, A100 GPUs, 4 per node, connected via NVLink, and then we have InfiniBand across nodes, and then this is the software setup. We evaluate different models, decoder-based models of different sizes, 160, 410, and 1 billion. And then this is the data set we use, and we compare different fine-tuning methods, both full fine-tuning and parameter efficient, and even quantized as well. So this is the throughput on a single GPU. So we see, compared to full fine-tuning, we get better performance on all of the model architectures. Right? So this is full fine-tuning, and then this is LoRa, and AdaLoRa, and then LoHa and LoKR. And then we see across all of these, we get better throughput, right? Because again, we are doing less computation in the backward pass. And this is evident in this pie chart, where we see that in the full fine-tuning, we spend around 2.5 seconds, and mostly it is in the backward pass, 65%. And in the LoRa method, we spend only 1.75 seconds, and we save on the backward pass time. So now, how does this translate to scalability when it comes to communication and distributing the workload across multiple GPUs? So this is a study on up to 32 GPUs, A100. With full fine-tuning, we see that we have a bad scaling efficiency, or relatively bad scaling efficiency. But with LoRa and the rest of the PEFT methods, we see better throughput, right? We see better speed up and like for the 32 GPUs, we see like 31.5x speed up. So that is very significant, which means that communication overhead is very, very small. And if we look at this chart here, the bar chart, is comparing full fine-tuning with LoRa on up to 32 GPUs. We see that the communication and overlap does not take any time in the iteration, the training iteration or the fine-tuning iteration. The reason for that is that we're only updating a very small subset of the model weight. So we calculate gradients for a small subset, and that means we only need to communicate the small subset, right? So the conclusion of this work is that if you use PEFT methods, you're going to expect very good scalability, right? At least with the distributed data parallelism. Now, for future work, we're also going to explore, in fact, we are already exploring more advanced parallelization strategies, such as FSDP, fully sharded data parallelism, and 3D parallelism, where we combine multiple parallelism strategies. And then with that, I conclude the talk. Let me know if you have any questions.